Okay, before we compose two functions f and g, and we can extend this process to compose any number of functions. So if we want to compose three functions, say f after g after h, we first compose g and h, and then apply f to them. So we get first h applied, then g after h, and then f after g after h. And we can do this for any number of functions. We have fn after fn minus 1, after fn minus 2, etc., etc. After f1 of x is, first we apply f1, then we apply f2 to the result, then f3, and so on, and we carry on until we get to the nth function. The domain of a multiple composition like this is the set of all x, so that I can first apply f1, so it's x in the domain of f1, and then I must have f1 of x is in the domain of f2, because I'm going to have to apply f2 to f1 of x, and then the next thing I get, f2 after f1, must be in the domain of the next function, f3, etc., etc. Fn minus 1, n minus 2, down as far as f1 of x, what I get when I've applied all of these, must be in the domain of the next function, fn. So these are the x values for which first of all f1 can be applied, and furthermore every successive evaluation gives us something in the domain of the next function. Let's take three functions and find their composition. So suppose f of x is x squared plus 1, g of x is the square root of x, and h of x is 1 over x minus 3. What's f after g after h of x? Well, according to the definition, f after g after h of x is, first I apply h of x, then I apply g of x to that, and then I apply f to the result. And so this is equal to, taking this in steps, f of g, and I'll work from the inside out, of h of x, which is f of g of 1 over x minus 3. And now I apply g to 1 over x minus 3, so I'm going to go to f of the square root of 1 over x minus 3. What is f? That's x squared plus 1, so this is the square root of 1 over x minus 3 squared plus 1. And that's just 1 over x minus 3 plus 1. And when I add those, the common denominator is x minus 3. So it's 1 plus x minus 3 plus 1 over that, and that's x minus 2 over x minus 3. That's my formula. Now what about the domain? Well, certainly this domain's not going to contain x equals 3, but let's see what it is using our description of the domain. So the domain of f after g after h is the set of all x to which first of all I can apply h, so it's x in the domain of h, such that when I apply h, I get something in the domain of the next function g, and when I apply g to that, I get something in the domain of the next function I apply, which is f. Now you see the domain of f is everything from minus infinity to infinity. Domain of g is everything from 0 to infinity. And the domain of h is everything except 3. So now my domain of f after g after h is equal to x in the domain of h, so it's x in everything except 3, such that what? Such that when I apply h to it, I get something in the domain of g, which is everything from 0 to infinity, and so that g of h of x is in the domain of f, which is just something, anything in the real numbers. So that's not really a restriction. So let's see what this is. This is everything except 3. 3 is ruled out to start with. So that h of x, what is h of x? So that 1 over x minus 3 is greater than or equal to 0. And g of h of x, which would be the square root of 1 over x minus 3, is just something, some real number. Well, that's not going to be a problem. Here's the problem right here. So I have any x value which is definitely not 3, for which 1 over x minus 3 is greater than or equal to 0. Well, I must have x greater than or equal to 3 here for this thing to happen. So it must be in this part. It's from 3 to infinity, but I'm not allowed use 3 because 3 is not in the domain of h. So it's every x excluding 3 for which x is bigger than or equal to 3, and the square root of 1 over x minus 3 is a real number. Well, that's not really a restriction. So this ends up being all numbers from 3 to infinity, not including 3. Okay, I suppose I want to calculate f after g after h of 12. Now I did have a formula there, so I have f after g after h of 12 is equal to 12 minus 2 over 12 minus 3, according to this formula that I derived. And that's equal to 10 over 9. And that's it. F after g after h of 12 is 10 over 9. Now you may also need to unravel 3 functions that have been applied consecutively when you use the chain rule. So here's an example where you have to find 3 functions, f and g and h, so that their composition is 44 plus x squared plus 4 to the 100. So again, you're going to do this in steps. So we want f after g after h of x, which is f applied to g after h of x, and we want that to be equal to 44 plus x squared plus 4 to the 100. So again, there's a bit of guesswork. Starting inside the brackets is a good place to go. So I'm going to try for h of x equals x squared plus 4. And now the next step would be to raise that to the power of 100. So I'm going to let g of x be the power function, x to the 100. And finally, I'm going to let f be the function which just adds 44 to anything. So f of x is 44 plus x. Let's check it out. When I take f of g of h of x, I get that that's f of g of x squared plus 4. And I do know that g of x squared plus 4 is x squared plus 4 to to the 100. I'm looking at f of that, and f just adds 44 to anything to which I apply it to. So f of that's 44 plus x squared plus 4 to the 100. So that is indeed the correct composition of functions. So I've broken this expression down into a composition of functions. And doing this is very important when we get to the chain rule in calculus.